Existence University is committed to free minds and to the highest quality of content, and as such, we will never take government or corporate financial support. The following is brought to you by Existence University merchandise, available at the Patreon page You Exist, and also by donations through PayPal or Patreon by viewers like you. Thank you.
The key to the next revolution in physics has been hiding in plain sight for over a century. Let's find out what that key is here on Inductica.
We've been living in sin so long, all the feels are gone. Fella stopped me on the street last night, said everything's
So what is the value of keeping your mind connected to the fact, knowing what's actually the case,
It seems your meal ticket is
knowing
gone.
what's true in reality?
Life goes on. I could never imagine something better. Yeah, right. Now you're cooking on high heat in the middle of the street. Roller coaster, take me to a better time. Let's go. All sing your high line with the roller coaster of life. It's time to all choose your timeline on the roller coaster of life. You seem to easily forget how to place your bet. When everyday life gets you down, you gotta steal the crown. Got to own it. Don't bitch and moan about it, please. God forbid you scrape your knees, and it's nothing to sneeze at. Oh, I've told you over and over again. You gotta get both hands around it and make your own plans. Roller coaster, it's taking over, it's about time. Oh, oh, sing your high line on the roller coaster of life. You've got to all choose your timeline with the roller coaster of life. Roller coaster. I want to go down the rabbit hole, down the rabbit hole of life. And now it's about to leave. Oh, roller coaster.
First, and most importantly, this experiment doesn't explain how waves can exist where nothing is waving. So I want you to keep that firmly in mind, that that's the ultimate argument for the ether, is that something has to be waving.
This is labeling alternative belief systems as illegitimate, evil, or not useful. This is a cult attack that the others are useless, when in fact, the experiments are not even what he claims they are about.
But second, it's worth noting that the physicist Heinrich Lorentz was actually able to explain this negative result using the ether.
This is another oversimplification and/or a lie. It's deliberately withholding a ton of information in order to project his point.
Using Maxwell's equations of electricity and magnetism, Lorentz calculated that the electromagnetic field produced by the atomic nucleus would change depending on the nucleus's state of motion.
Here again we see a giant oversimplification. In fact, let me just show you one page from what he's talking about. Does this look as simple as he's suggesting? Here in fact we see that Lorentz actually writes I am far from wanting to attach too much importance on the preceding considerations.
This change in the field of the nucleus would change the circular orbit of the electron.
Oversimplification. What circular orbit? Which century of atoms are we talking about? Because we no longer have the planetary model of atoms. So what is this circular orbit? Today we have quantum clouds. This is another superposition of different centuries of science being smashed together. The quantum particle does not have circular orbits. And say that they did. The Earth is moving, so every particle we have ever seen was in motion. There is no such thing as the stationary frame.
Into this elliptical smashed orbit like this. Now, since Michelson and Morley's table is of course made out of atoms, this would cause the table to get smashed by this exact same amount, shortening the distance that beam B must travel.
Given that there is no such thing as the stationary frame, there would be no model of the Michelson-Morley experiment where the apparatus ever had a perfectly circular apparatus. The Earth was always moving. So it doesn't make sense to just squish it in the direction of the ether. It's also being squished in the direction of any movement the Earth is making, which is the revolving of a day and the revolution of a year.
Now, upon doing the calculations, Lorentz found that the change in length of the table along the direction of the ether motion would shorten the path of the beam just enough to cancel the amount that the ether wind would slow that beam down.
This model only really makes sense on a flat, stationary Earth. The problem really is that James is smashing together a century's amount of work in order to create a picture which is better setting up his version of reality, but in fact, he's borrowing things that should not ever be smashed together,
making it appear to be going the same speed as the unaffected beam. Now, today, of course, we know that length contraction is real.
Here's the thing, though. James himself does not actually believe in length contraction or time dilation, so he's merely setting up a frozen abstraction or stolen concept so that he can later deny the very thing he's saying we know is true.
Contrary to the normal narrative that Michelson-Morley disproves the ether, Lorentz actually discovered length contraction before Einstein by using the ether to explain the Michelson-Morley experiment.
This is just, in a sense, historically inaccurate. He's painting a picture in the way he wants the picture to be painted, but he is lacking all historical accounts and providing us no citation to go with it. Therefore, allow me to provide the historical context. Note the repeated use of the word luminiferous in the term luminiferous ether. The luminiferous part of that term is entirely in regard to how light travels through the universe. Quoting Einstein, the man who is said to be the slayer of the ether, we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable. For in such space, there not only would be no propagation of light, but also no possibility of existence for standards of space and time.
So, if Lorentz discovered length contraction, then why is Einstein the one who's remembered for it?
It has to do with what you do with ideas, not just the ability to, say, come up with them. It's kind of like this. It's like saying, if Native Americans lived in the Americas before the discovery by Amerigo Vespucci, then why do we give credit to explorers like Amerigo for discovering America? Because there's a huge difference between stumbling upon something and not knowing how you got there, and navigating the hardest aspects of a journey to document and understand every aspect of how to get from point A to point B.
Einstein ditched the ether and instead derived length contraction from the assumption that light is measured to be the same speed for all non-accelerating observers, regardless of their speed.
This is not an assumption. This was a known fact since James Bradley in 1725, almost 200 years before Einstein was even born. The Cartesian and Huygens theory can be said to be a vortex theory. Boyle and Hooke have a stationary ether, and Newton, though stating that not having an ether is absurd, his math didn't need one and spawned a purely mechanical motion of planets. Every form of wave theory or corpuscular debunking of wave theory was assumed that the waves were longitudinal waves like that of sound. In 1725, James Bradley conducted an experiment that was attempted by two other scientists on different occasions. The experiment was to measure the parallax of a fixed star in order to prove the Copernican model. The star was chosen for the reason that it never sets in England, the country of its measurement, and it passes directly overhead at some point of the day or night. Molyneux's telescope was built to Hooke's description, but Bradley had to have a smaller one constructed after Molyneux died in order to fit it into his observatory. The experiment was to detect stellar parallax, which is an apparent change in the position of a star due to the relative position of the Earth as it orbits the Sun. Bradley expected to find he would have to move his telescope in a circle as Earth circled the Sun, as that motion would make it look like the star is moving in a small circle. What Bradley found, however, was that he would have to move the telescope only half of the year. For one part of the year, the telescope had to be pointing slightly in one direction, hitting a maximum of 20 arc seconds. Then it would return back to 0 arc seconds 4 months later. Then, 4 months later again, he needed to move the telescope to a maximum of 20 arc seconds in the opposite direction. And again, 4 months later, it returned back to 0. And then 4 more, and back to the 20 arc seconds in the first direction. This observations of Bradley's was given a new term, called stellar aberration. And Bradley explained it with a simple analogy. If rain is falling straight down, a man standing still in the rain would see it fall straight down. And if the man jumps straight up and down, he will still see the rain fall straight down. But if the man walks perpendicular to the falling rain, he will have to tilt his umbrella in the direction of his motion in order to stay dry. This is caused by the same Galilean effect as dropping a cannonball from the mast. If the raindrop is 10 feet away when it is at eye level, and is at 0 feet away when it is at foot level, then it appears that the raindrop has moved towards you at a slope. You don't have to worry so much about the rain that is currently above your head, as it will be behind you before it can hit you. This also means that it is the velocity of the observer that causes this apparent position of the star, not the observer's position, which would have been parallax. In September, the Earth is moving at its most perpendicular to the parallel light rays of Gamma Draconis to the north, and the telescope needs to be tilted a tiny amount towards the north. To get an idea of the small amount of tilt, here is a 20 arc second difference, and here is a degree difference. In December, Bradley's zenith is moving towards the star and is parallel with the light rays, and therefore the telescope can see the star at 0 arc seconds from zenith. In March, the Earth is moving perpendicular, in the opposite direction it was from September, and the telescope needs to be tilted in the opposite direction from the September measurements. In June, the Earth is moving away, in parallel with the light rays, and the telescope can again see the star at 0 arc seconds. Bradley explained the results of his experiments with the corpuscular theory of light, as the light was acting similar to raindrops falling. Using this idea, Bradley, in 1728, was able to make speed of light measurements, which were relatively close to the ones we know today. But more than that, Bradley discovered that the speed of light was a constant, as light from every star arrived at the same velocity. It may not seem like it today, but this discovery had profound implications. The idea that the speed of light didn't appear to change meant that the ether is stationary in the Earth's frame of reference, which is strange, as the Earth is always changing directions as it orbits the Sun. The effects of aberration will not be explained for another 200 years, and all those years are spent trying to explain how to fit stellar aberration into the other theories.
The way this assumption is usually explained is that if you take two observers, one stationary, another on board a spaceship traveling at half the speed of light, and the moving observer shines a flashlight, then that moving observer will measure the light as running away from him at c, the speed of light. Now, common sense would then tell you that the stationary observer would observe the light moving at 1.5 times the speed of light.
Well, it is a very good idea that we do not use common sense as a scientific tool, isn't it?
But Einstein's assumption states,
it is not an assumption to say that the speed of light is a constant and that physics works.
That the stationary observer will also observe the speed of light to be going at the same speed as the moving observer, that is, c.
That is to say that the stationary observer, which both parties can equally claim to be, experiences causality as occurring as usual. That's all it means to say that the speed of light is c. It means both parties experience reality normally.
Now, the way Einstein explains length contraction is by saying that this strange way that light is measured by different observers to be going the same speeds then requires those different observers to also measure different lengths.
Given that James either does not understand or is intentionally leaving out information, let me show you the truth. This brings us back to the solution to the Maxwell-Galileo problem. We said earlier, the only way to satisfy electrodynamics and the Galilean principle of relativity at the same time is if space and time are relative, as charge is invariant and does not change with respect to motion. We now know that velocity of objects must be relative to observers, as this means that different observers see the same events in space at different times. So we get two investigators, and they are placed in different frames of reference. One investigator is riding the wire. The other is riding the charged particle. Both investigators agree that 1. Someone is moving. 2. The particle and the wire move further apart after some time t. 3. Both agree that the speed of light is c. And 4. That physics is working. They are not exploding on-causally. Special relativity. The manner in which to apply these equations, known as the Lorentz transformations, is similar to applying the Galilean transformations. In Galilean relativity, we saw that the speed of a thrown object was added or subtracted from the speed of the object it was thrown from, in order to have our math match reality and conform to each person's point of view. If a man on the shore wanted to know why the sailor thought the ball was only moving at 50 kilometers an hour, he had to remember that the sailor forgot about the relative motion of the ship. So the man on the shore subtracts the ship's motion and gets the same answer as the sailor, and vice versa. Lorentz transformations make clear that the ether is basically a fixed quantum field and light travels through it at the same speed in all directions, and matter which interacts with that light also travels through it, but the light is only attached to the ether, so the motion of the matter does not change the speed of light. Because of this, you apply the Lorentz transformation by remembering that the sailor of the spaceship, which travels at the speed of 0.7 c, forgets about the relative motion of the ship. And so the man on the planet has to multiply the sailor's measurements of time and distance by a factor which keeps the speed of light constant. This provides us with the definitions of proper time and proper length. Proper time. The time that elapses in the frame in which events all occur at the same location. Proper length. The length of an object in the frame in which events all occur at the same time. Alice and Bob are our two investigators. Alice stands on a train platform, holding an extended rod affixed to a flashbulb in each hand, which she is extending a total of 2 meters apart, in an east-west direction. Alice, using her brain, fires a neuron signal which is to have both hands turn on the flashbulbs at the same time. The light which is emitted from the flashbulbs will reach Alice's eyes at the same time. As light must always travel at the same speed in the same medium, then the flashbulbs must be equally far apart from her eyes, and the lights, from Alice's perspective, can be said to be emitted simultaneously. Bob is on a moving train, adjacent to the platform. Bob is moving at 0.7 c eastward relative to Alice. If Alice is seeing both lights at the same time, then before Bob can see Alice at all, as the lights have not yet reached Bob, he uses his smarts and does the math. Since the speed of light is c always, since Alice has the two flashbulbs 2 meters apart, since Alice appears to be moving at -v, then the light moving -c must take longer to reach the left side of the platform than the light moving +c reaches the right side of the platform. Therefore, if Bob believes Alice when she reports that she saw both lights, requires for Bob that the lights were turned on at different times. Bob would find Alice had to have turned on the east light first, then much later turned on the west light. Bob checks their math. According to Alice, the two light bulbs are 2 meters apart, and they reach her at a time difference of 0. So Bob plugs this into the formula. The difference in time between the lights turning on for Bob is equal to gamma times the velocity of the train divided by the speed of light squared times 2 meters plus 0. Since Alice is moving, according to Bob, at -0.7 c, Bob finds a time difference of light flashes must have been 6 nanoseconds apart. Bob takes the flashbulbs, and they repeat the experiment. Bob now sees the light reach him at the same time. So what will Alice find when she checks her math and diagram? When Alice has the lights, she reports that the lights reach her at the same time, 0 nanoseconds apart. And she did so because she pressed the buttons at the same time. Bob argues that Alice must be mistaken, that if the first statement is true, then Alice must have triggered the eastmost light 6 nanoseconds earlier than the westmost light, as light cannot violate causality. When Bob has the lights, he reports that the lights reach him at the same time, 0 nanoseconds apart. And they did so because he pressed the buttons at the same time. Alice argues that Bob must be mistaken, that if that first statement is true, then Bob must have triggered the westmost light 6 nanoseconds earlier than the eastmost light, as light cannot violate causality. Alice and Bob both agree that the other's far light had to have been switched on first, but both say that they turned their lights on at the same time. One possibility is that the far hand experiences time differently than the close hand. Perhaps this is a brain effect. Maybe our right hands attempt to balance out neural length differences with a default 6 nanosecond delay. Unfortunately, this cannot be true, as the delay again shows up if we switch directions, and then it is the left hand that appears to experience that time delay. Still, maybe it is a brain effect, where the hand furthest from the forwardness is delayed for some reason. So Alice and Bob construct a new experiment. No hand switches to remove this possible bias. Instead, Alice and Bob fix clocks to their east and west walls. According to each investigator, they see their own clocks as ticking at the same time, reading the same time at the same pace. However, the other experimenter must disagree that their clocks are synced. Despite not being able to see the other person's results, as the light takes too long to reach them, they know that the light that traveled in the direction of motion must have come from an earlier time, according to them, as the light from the back end takes longer to reach the investigator in the center. So both investigators know that their clocks appear to read the same time simultaneously, but they must also know that since one or both of them is in motion, then the light moving in the same direction as their motion must have been emitted earlier than it would appear. And therefore, if they approach the clock on the back end, they would see it speed up as they move towards its proper time. So the clock in the front is actually behind, and the clock in the back is actually ahead, such that the difference in distance the light needs to travel to reach the investigators balances out to appear to arrive at the same time. This is because light travels through the quantum photon field, or ether, as opposed to being a type of object that experiences time and space. Light is not contained in the ship like the air and man and ball and flies and fish were. This clock setup is merely another example of the relativity of simultaneity. The lights coming from the flashbulbs or clocks were emitted or reflected at different locations at different times. A weirder effect occurs when the two investigators, within their own frame of reference, record the same time, but based on the travel distance of a mover, the other must calculate that the other's clock is moving further. So if they are recording 1 second, and you know it traveled more than 1 second amount, their clock must be slow. One of the thought experiments that demonstrates this is called the light clock, which is a perfect mirror box that has a trapped photon inside, such that the photon of light bounces up and down in the box, and each time the photon does a number of bounces, it counts out the seconds of a normal clock. As a simple example, 1 second may be counted when the photon does one complete trip from the top to the bottom and back to the top. In reality, such a clock would require millions of bounces to count 1 second, as light moves at 3 × 10⁸ meters per second. So if the box were half a meter tall, then one complete trip would be 1 meter, and so to count 1 second would require 300 million complete trips, or 600 million minus 1 bounces. I have a different clock that we can use. It's our neurons. A lot of your nerve cells have a long cord called an axon, and that axon is insulated with what is called a myelin sheath. The axon is long, such that a single cell can reach far across the body to communicate its signal, and the myelin sheath helps to make that signal move faster. Together, the signal of touch can move at 80 to 120 meters per second. As most people are between 1 and 2 meters, a 100 meter per second signal can travel up and down the average person 50 to 100 times in 1 second. For a signal to be felt, it does not need to travel all the way to the brain. Some signals can be felt at the moment the signal reaches the spine, such as the knee-jerk reaction or reflex. So imagine Bob is 2 meters tall. His legs are equal in length to his torso and head, making his legs 1 meter long. As Bob moves along inside the train, which is moving at 0.7 c, Bob feels a pebble in his shoe. If we were to set up a neurology lab in the train and hook Bob up to an EEG machine to test his nerve impulses, we see that Bob's signal moves at 100 meters per second, or 0.1 meters per millisecond. So it takes 10 milliseconds for the signal to move from the foot to the spine. If we repeat this neurology lab in the stationary frame, Bob's nerves still receive the signal after 10 milliseconds. So we can say that Bob's nerves are constant. They always receive the signal in the same period of time, 10 milliseconds to travel 1 meter. But Alice is not convinced. Alice never got on the train and never saw the lab being done, but she trusts her colleagues would not make such a mistake. But clearly something is wrong. For when Bob was on the train, The signal that started in his foot traveled straight up his leg to his spine in 10 milliseconds, but his spine was no longer 1 meter away. After the first millisecond, the spine, Bob, and train had moved 210,000 meters eastward. If Alice calculates how long according to her clock it should have taken the signal to travel, given the motion of Bob and his train, Alice must argue that by her clock, it would have had to take longer than 10 milliseconds. However, Bob counters and says that from his point of view, it was Alice who had the nerve signal that took longer than 10 milliseconds to be received. Given that he has the lab equipment using electrical signals that move at the speed of causality, he argues that it cannot be wrong that it took him 10 milliseconds, whether his frame is moving or not. And he argues that it was in fact Alice receiving nerve signals slowly, and therefore experiencing time slowly, and therefore seeing him slowly. If relative motion affected the speed of our nervous system, we would never move, as every time we started moving with a constant velocity that is different from the stationary Earth frame of reference, our nerves would fail to function properly and we would die, unable to signal the heart to beat and lungs to breathe. There is only one solution that solves the conflict. Velocity is relative, simultaneity is relative, and now we also know that time is relative. We already found the math that will help Alice find the time difference. According to Bob, his clock says 10 milliseconds, so she needs to write the equation delta t prime equals gamma times delta t. Delta t is Bob's time according to Bob, 10 milliseconds. And when Alice plugs that in, she finds that it actually took 14 milliseconds. Since Bob thinks he is stationary and therefore gets 10 milliseconds, Alice accounts for his motion, just like in Galilean relativity, and gets that Bob's clock is actually ticking slow relative to hers, not that his nerves are speeding up. Bob cannot witness this because Bob, his nervous system, his clocks, everything at that velocity is experiencing time differently from Alice. But according to Alice, Bob's clocks reach 10 milliseconds after what is really, in the Earth frame, 14 milliseconds. Since velocity is relative, and velocity is distance over time, and time is relative, we have to ask, is distance also relative? We can check if distance or length is relative. Distance is length between 2 points, typically associated with velocity and the time it takes to get places. But distance itself can be represented with a static map, such that the time of measuring distance on the map would make no difference. Two houses a mile apart remain a mile apart on the map, no matter how fast you move objects on the map, or what time of day you measure it. Therefore, if we want to know the length of an object, we can make it sit still, and measure its top, and then its bottom, at different times or days, but since it's not moving, that's okay. One of the issues with length in these cases is how do you measure a length when it's moving? For instance, when you have a map that shows two houses are 1 mile apart, it doesn't matter how fast you move toy cars on the map. The distance is the same. What if you move the map around very fast? Does the distance change now? As, by the time you have a chance to move your eyes to the other end of the ruler, the location changed, including the first end, which is no longer at the first house. We found that if an object is in motion, then the two frames of reference will argue over whether or not their clocks were synchronized or not, and this causes an issue in the agreement of length measurement. So if we want to measure length, human clocks and rods will not be very useful to us. Instead, we can use the properties of light to get what we want. Light always travels at the same speed, so we don't have to worry about whether the velocity is relative. Given that, Alice and Bob set up a new experiment. Alice and Bob fix a laser pointer at the back of their trains, and a mirror at the front ends. The laser is fired across the train length, hits the mirror, and returns back to the source at the back wall. The length of the train is therefore the distance the light traveled, and the time it takes to travel is the distance divided by how fast it traveled it. So for Alice, who is stationary on the earth at the train station, the light traverses the inside of her train without the train itself moving, and so the distance the light needs to travel is the train's length twice, and its change in time can be found by dividing the twice train length by the speed of light c. Bob disagrees because to him Alice is in motion, and Bob states that to him he is motionless, and her calculations are actually his, that it took his photons twice the length of the train divided by c. But Alice knows that it is Bob that is in motion, and so Alice does the math to check what is happening here. According to Alice, when Bob's train's back end lines up with hers, it fires a photon towards the front of the train. But the train is moving in the same direction of that photon. So the photon approaching the front of the train must travel the distance of the whole train, plus the distance the train moved in that time period. Once the photon hits the mirror and starts to return to the back of the train, the distance it would have had to travel would be the length of the train. However, before it can do so, the back of the train races up to meet the light, and so the second photon travels the length of the train minus the distance the train moved in that time period. She finds that the change in time of the moving train must be gamma squared times the stationary frame of L2 over c. If Alice used the relativity equation of change in time of one frame of reference for another, and she plugs in the equations her and Bob found, then Alice comes to find that the length of a moving train is less than the length of a stationary train. When we get Bob moving at 0.866 c, Bob and his train reduce in length by a half. Bob's 2-meter-long train is now 1 meter in length as he moves. Of course, to Bob, he is normal, he is not moving, and Alice is the one that appears to be reduced in length, in the direction of her motion, by half. Einstein's discovery that the Galilean principle of relativity had a special case, due to the nature of light, demonstrated that the principle of relativity said more than just velocity is relative, and showed that it also proves that simultaneity is relative, time is relative, and distance and length are relative. Therefore, Einstein used this discovery to show that Maxwell's electrodynamics does not have a relativity problem, just a Galilean relativity problem. By involving a simple parameter, gamma, Galilean relativity becomes more powerful, and can now deal with objects moving near the speed of light. Einstein showed then that the charged particle, from its point of view, is stationary. However, the wire which appears to be moving is reduced in length, and therefore has more positive charges closer together, and therefore the wire appears to have an electric field, which interacts with the electric field of the positively charged particle, and therefore is repelled away from the wire. This solved the Maxwell-Galilean relativity problem. Just like with the Galilean principle of relativity, if you assume it to be false, then you would have to accept that every event involving velocity would have 2 or more causal realities, such that to one group of people, the ball was thrown backwards, and to another group of people, the ball was thrown forward. Likewise, if you assume the special theory of relativity is false, then you must accept that 2 or more causal realities split from the event every time an object or photon moves. Without requiring the assumptions of many worlds, special relativity answers the question of what time and length mean to moving objects, and does so without violating causality. Since causality is the one big thing we really cannot violate, then the special theory of relativity must be accepted as true. The alternative is to violate causality or to form many worlds for each and every velocity. Let us leave off with a real-life example. The sun sends out high-energy particles that move through space at near the speed of light, and upon hitting the Earth become a bunch of secondary particles, one of which is called a muon. The muon is an unstable subatomic particle, which has a mean lifetime of 2.2 microseconds. Given the short lifespan of a muon, under regular Galilean relativity, the muon would decay before it can reach the ground. However, muons reach the ground all the time. Given the distance they have to travel from creation to annihilation, from the atmosphere to the ground, the speed and lifetime of the particle is too small to survive all the way to the ground. Calculations show that it would take 6.4 microseconds at its speed to reach the ground. So how are they doing it all the time? Well, the muon is traveling at 0.99 c. So from the ground, we would see that the muon's clock is slow and is ticking to 2.2 microseconds in what to us is actually about 10 microseconds. And to the muon, it appears that the distance between the atmosphere and the ground has reduced from 2,000 meters high to 280 meters high, so it can reach the ground in 2.2 microseconds. If time dilation and length contraction were not facts about the nature of motion, then nearly all of the muons would decay in the upper atmosphere, which is not something we experience. Let us review our list of principles. Existence exists. A is A. Consciousness is conscious. The universe is causal. The universe is full. Nothing is prior to the little stuff. The Galilean principle of relativity is valid. Light is an electromagnetic energy disturbance in the electromagnetic or photon field, which always travels at a constant velocity in the ether because of the properties of the ether. The special principle of relativity is valid.
That's Einstein's way of explaining it with this assumption that the speed of light is always measured the same speed by different observers. So both Einstein and Lorentz's theories are consistent with experiments. But Einstein's theory was accepted on the basis that it made fewer assumptions.
It has nothing to do with Occam's razor. It is not that Einstein has less assumptions. It's that Einstein proved he was correct.
Instead of positing that length contraction and duration dilation are caused by a difference in motion through an ether that we can't even measure the speed of, all of the interesting effects of what is now known as special relativity could simply be deduced from these two postulates of Einstein's: that the laws of physics are the same for all non-accelerating observers, and that all of these observers measure the same speed of light.
So instead of positing that length contraction and time dilation are caused by difference in motion, we could instead deduce from Einstein's postulate that when things move, time dilation and length contraction are the results? No, is that not the same thing repeated? What is he trying to say? Existence University is committed to free minds and to the highest quality of content, and as such, we will never take government or corporate financial support. The following is brought to you by Existence University merchandise, available at the Patreon page You Exist, and also by donations through PayPal or Patreon by viewers like you. Thank you.